So on Monday, we will continue this. We've also got a video for you on Monday. And then we'll kind of wrap this all up on Tuesday with one last thing. Wednesday will be a little bit of everything practice day. Next Thursday, you will have a quiz specifically on light and electrons and how those things interplay. After you are done with your quiz on Thursday, we are going to give you the remainder of the time to work on finishing your lab report. Remember again that there are some parts that you're going to need to copy and paste on the from the Google Doc, create your own, print and color, all right? If you were not here yesterday, makeup is Monday after school, so you guys will get you caught up. I think that's it. So everything's on Google Classroom for you. That's the other thing. We did ask for you to watch the electron video, all right, and create and complete the Google form for that. That was due Wednesday. Got that all in the grade book yesterday. If you didn't do it, I'm sorry, you didn't do it. Yeah, and that's where we are at this point, all right? We are getting close to the end, so next week will be some practice and wrapping up, and then the following week will be the practice test and real test. All right, that's where we're at. Okay, so we can go.
Starting.
Yeah.
All right, so as Simpson said, we're gonna start combining some of the concepts that we've talked about this week. It's probably seemed a little random that we started with electrons on Monday, and we kind of morphed that into light in our EMS spectrum. And we're gonna kind of now combine these terms and see how they are related. First things first, let's do a little bit of a turn and talk, okay, refresh our minds, specifically on electrons. So you should have these questions on your sheet so you can kind of jot down the answers. But I'd like you to turn to the people in your pods and kind of discuss these. Give you guys a few minutes to talk about them, and then I'm gonna pull sticks. So be comfortable with some of the answers. If you don't know the answer, ask somebody next to you so that if I pull your stick, you are ready to go. Okay? All right, go ahead. Give you guys like 3 to 5 minutes. We'll see how long it takes. There should be talking, turning and talking, yes? Not silence?
Talk to each other.
You can, no, I wanted her to. She wanted to see like a transition like between.
Oh, okay.
So. Definitely turning and talking. It's so quiet. We're proud of you for showing up today. Come on, put some effort into being here.
What is it? It is subatomic particle with a negative charge. I know where it is. The electron cloud.
I tell her when to, if there's gaps and whatnot between, so she can always.
Right. I didn't know if you just.
No, it's hard to edit it and stuff. So unless I have a paid app, I realized I tried to do this last year. So
What about on iMovie?
tried. It was awful.
Oh, okay.
It was awful.
Valence electrons are like the extra electrons that are allowed in most of them.
I don't remember. Talk to each other.
give you guys like a minute more. Make sure you have an answer to each of these questions. Pull all the absent people this time. All right, let's wrap it up. Let's bring it back in. All right, so we should have answered these questions on electrons. This should be a recap for you. So first question, what are they and where are they located? Bailey.
They're negatively charged particles within an atom, and they're located in the electron cloud.
Perfect. Exactly what I was looking for. Negatively charged, located in the electron cloud, which is around the nucleus of our atom. Fantastic. All right, what is their charge? We kind of already answered that. I don't think in this class we touched as much on electron mass. I don't think so. But does anybody know the answer? Or has a guess? Not you. No one? That's okay. It's so very, 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 very tiny that it's almost insignificant, okay, mass-wise, okay? A lot of our mass is coming from our nucleus. If you remember watching that video on how small is an atom, we talked about the density of a nucleus and how that is incredibly dense, and that's where a lot of our mass is sitting. Electrons have little to no mass, if that's what you want to write down for that answer. All right, what model do we use to visualize electrons? Cece.
The Bohr model.
The Bohr model. And is the Bohr model correct? When you look at the Bohr model, is it 100% accurate to what's actually happening around the atom? Theo? No? Why?
Because you asked the question as well.
Yeah, okay. So we visualize the Bohr model, right, as those little perfect rings, those energy levels. Okay, that's not actually how it's happening. Okay, it's a little bit more sporadic. And if you can kind of look over at this image here, this is a little bit, still not perfectly accurate, but you can see kind of like a wavy motion, kind of symbolizing that it's not a perfect circle. So, yes, no, they would not. It's not 100% accurate, but it's a great visual model to be able to tell where our electrons are. All right, valence electrons, what are they and how do we find them? Nate.
Electrons in the outermost orbit involved in bonding,
Mhm.
and you can find out, you can determine how many there are by looking at the top of the columns in the Roman numeral.
Perfect. Do you remember which groups?
The A group.
A groups. Fantastic. Yep. Remember, we're not talking about B groups when it comes to valence electrons right now because it does really weird stuff. So, if we want to look at the periodic table to determine our valence electrons, we look at those A groups at the top of the column, and that Roman numeral symbolizes how many valence electrons the elements in that column contains. Very good. Good job. Great answers. We're going to do it again. Aren't you so excited? We're going to talk about light now. Okay, we recapped on electrons. Now let's recap on light, which was the past 2 days, Tuesday, Wednesday. So if you need your notes, please take those out. I'd like you to answer the questions. How do we organize light? What kind of light can we see? Define frequency and wavelength. What types of light did we discuss? And how many types are there? What's the relationship between wavelength and frequency? And what does all light have in common? So yes, take out your notes, but remember also be turning and talking to your pod mates. Give you a couple minutes to do that. Get some thorough answers.
Also frequency.
So there's no talking. Talk to each other. Please. Heard the no. Hey, I'm just happy they're here today. This is probably the most people we're gonna see in the class. It's also mostly sophomore. I feel like that makes a difference too. Oh, Colin responded to me, which was fantastic. But the answer, he pretty much said like they rebudgeted, so like they're trying to get rid of stuff. So he talked about trying to get some sort of guest speaker in for. I'm wondering, like, here's the thing. I have a lot of friends and connections, so it's not relevant to this. But he was talking about younger, trying to coordinate somebody to come in. I think it's cheating if I get my husband to come in and talk about working in a medical laboratory.
My husband does, his is totally bio, he's a pre-med major, he's
Okay.
in, not pharma, he's in medical sales. So like right now, it's a grafting thing where they actually harvest your skin, they basically mash it down, create a suspension, and then they spray it back on, so like.
Yeah, that's weird. I hate that, but
No, but like instead of having to do these huge grafts,
Radiation.
taking and moving, you're taking, like it's an 80-to-1 ratio.
it's
And so
wild.
you're using your own skin, so like it works really well for pigmentation to like alien populations. So that like especially they have like a base and they don't have these white splotches, they actually have their own skin pigmentation. I could see it,
See what I'm wondering, like I'd have to coordinate that with like shit, like that would be something for like your pre-med club, you know what I mean? Like a pre-med.
yeah, I mean he could,
We'll see.
we could,
Yeah,
we
let's
could.
figure All right, let's wrap up our writing, I guess. There wasn't a lot of talking, but we shall see what we know. All right. First question, how do we organize light? Austin.
Wait, no, me.
Yeah.
Wavelength and frequency.
We do, yes. Let's take it a little further. What do we look at to organize this light?
The wavelength.
Yeah, what's it called? Can anybody help him out? We did this on Wednesday. A little chart. What's it called?
Spectrum.
The electromagnetic spectrum.
Yeah.
Yes, that's how we organize and categorize our light, right? Okay, based off of wavelength and frequency, yes, that is correct, but we look at it through the EMS spectrum. Perfect. What kind of light can we see? Nora? Visible light. Very straightforward. It's in the name, right? Visible light. Okay, what is frequency and what is wavelength? Hudson?
Is frequency the intensity of the light?
Not the light. Let's talk, when we're talking about frequency, let's talk about the wave. So what is happening with the wave with frequency? Who can help him out? Jackson?
Number of waves per like the unit of time. Like
Yeah,
seconds.
yeah, number of ways per passing through that equilibrium. Yep, we talked about that. Fantastic. What about wavelength?
Distance between the crests.
Yeah, between either the crest and the crest of the wave or the trough and the trough. Okay, it's in the name, wavelength, right? Looking at that distance between. Fantastic. All right, what types of light did we discuss? How many types are there? Ethan?
Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray.
Fantastic. And that equals 7 types of light that we talked about. Amazing. All right, what's the relationship between wavelength and frequency? Theo? And vice versa. What kind, do you remember what kind of relationship that is? Inverse. Fantastic. An inverse relationship. All right, last one. What does all light have in common? Alyssa. Okay, who can help her out? Hayden. Speed. Do we remember what the speed is? What was our number for that? For speed of light? 10 to the
8
do you know the units?
meters per second.
Meters per second. Fantastic. Yep. All light has in common speed of light. And this could also be 3.00 as well. Both are correct. Are we good? Nice recap? Okay. Well, a lot of recapping before we touch on any new content today, because it's important that we acknowledge and understand all of these concepts. So, this is what we did a little bit on Tuesday and Wednesday, I believe. We did a little bit of both. We did our wave calculations, okay, with our little equation up here. So, we need to know what C is equal to. Does anybody remember what C is equal to? Huh. We may have just said it.
Speed.
Speed of light, right? So that's at 3.0 times 10 to the 8 meters per second, right? That's our speed. So speed is equal to our wavelength times our frequency. And in our question, we're going to have to find one of those. So we are given our frequency. A wave has a frequency of 5.2 times 10 to the 8 hertz. What is the wavelength and what type of wave is it? So if we know C as our speed of light, that's given, okay? We do not know our wavelength. That's what it's asking us for. Reminder that our wavelength units is going to be in meters. But we are given our frequency. Oh, I left it up there. Is that what you were laughing about? That might, oh, I didn't even notice. Okay. Frequency is 5.2 times 10 to the 8 hertz. So if we have all of our values, it's a plug and chug equation, right? So let me rewrite it out here. Reminder, if you set this up like this, which you should, and you use your units like this, you do not have to include them when you actually calculate it out and rewrite it. You have to include units in either here or in your actual calculation, one or the other. Since I already used my units, I'm going to leave them out. Okay, it's equal to our wavelength times 8. Who has a calculator and wants to please plug this in for me? Solving for wavelength. What we got? Hayden.
1.73.
Try one more time. One more time. 1.73. Tyler?
Is it 0.576?
Yes. 0.576 what? Meters. Nice. Cool. Fantastic. You calculated your wavelength. Okay, step one. There is a second part of this question though. What type of wave is it? So, this is where we're going to use our handy little EMS spectrum over here. So, I have my frequency, right? That was given to me. We can see that this was a times 10 to the 8th power. If I look down at my frequency here, okay, and I look at where times 10 to the 8th is, kind of follow that line up, okay, it's indicating that my wavelength should be for microwaves. Now, I realize that this says times 10 to the negative second, okay, and this is in decimal format here. If I rewrote this in scientific notation, it would look like this, so it would be to the negative 1. 10 to the negative 1, pretty close to 10 to the negative second. Yes. Some of you asked me during practice, because you had this issue where sometimes it kind of fell in between, especially for frequency sometimes. If it is really close like this, you can write out either the closest type of wave, or you could say, okay, it's between microwave and infrared, or microwave and radio. Does that make sense? Yes, because it's between those. Fantastic. So this would be microwave. All good? I can move forward? Awesome. Okay, now we're on to some new stuff. Talked about electrons and light separately, but now we're going to start putting them together. Okay? So electrons, they travel at the speed of light, 3 times 10 to the 8th meters per second, which sounds very similar to something else we've been talking about, I think. Electrons also travel like waves. Also very interesting. So we have these light particles that we call photons. Okay? These are what our electrons are acting as when we're traveling like waves. And we have this concept that's called duality, which we can say that electrons have duality. And what that means is that they act, see if I can write small enough, both like a wave and a particle. Because electrons are what? Are particles, right? Yes? But they travel at the speed of light, and they travel similar to waves. Do you want to prove this, Ms. Simpson?
All right, so we know that waves have certain, or I should say, we know that light is a wave because of a variety of things, primarily based on its following what we know about wave interactions. So there's 4 main types of interactions. There's reflection, so that's how a mirror works. Refraction, that's why like a straw or pencil is going to look broken in a glass of water. We have also what's called diffraction. I say reflection, refraction, diffraction, and interference. Okay, how to think about it. All right, so we know that light does all of those 4 things, therefore light has to be a wave, right? The other thing that light does, and this is where we're going to prove it behaves like a particle, and we call these particles photons. So, we can all agree, there we go. We can all agree that light is a wave, yes? Okay. We can all agree that the paint in a spray paint can are particles, yes? this is where we're gonna connect the light to particles. So if I had a can of spray paint, which the school would be very sad at me if I did this, and I sprayed it really close to the table here, would I get a small circle or a big circle? A small circle, right? Yes, we can all agree on that? And if I sprayed that really small circle there, would it be kind of light in color or would it be really intense? It'd be really intense. So when I hold it close, small, intense. If I moved back out here and I was farther away, what would it look like then? Would it still be a small circle? No, it'd be really big, yes? Would it still be intense? No, it would be more light in color, yes? All right, so let's take a look and see what happens to the flashlight. When I hold the flashlight really close to the demo table, I get a small, intense light, yes? Yes, we all agree on that? Like the paint can. If I pull the flashlight back out here away, much bigger and not very intense, yes? So this is how we can prove, that light also contains particles. Questions, comments, concerns?
Thumbs up, thumbs down, sideways.
Awesome.
I like that demo. I also like how you do it better. Timing, I got 10 minutes, I think. No, I don't. I don't have 10 minutes.
You have 7 minutes.
I have 7 minutes. Let's do this really fast. Really fast. Like 2 minutes. 2 minutes. Turn and talk. Or not, because you guys are a little quiet today. Or write them down. Okay? We talked about now our relationship between light and electrons. Discuss some similarities between light and electrons. There's 2 major ones, and we've kind of given you a sentence starter here to help you. So, actually, I'm just giving you a minute. So, go.
Yeah, both are waves and both move at the speed of light.
Fantastic.
I said that both can be active, both particles and waves, and both move at the same speed. I did say the second one correct.
Are we feeling pretty good? Yes? I guess that wasn't really a minute. That was like 40 seconds, but I believe in you. Okay. Discuss some of our similarities between light and electrons. The 2 major ones. I just discussed them. Ms. Simpson just demoed them for you. So, they both travel at what, Chelsea? Speed of light. Fantastic. Speed of light, 3.0 times 10 to the 8th meters per second. And they both travel as, Jackson.
Particles and waves.
What was that term called? Do you remember?
Duality.
Duality. Nice. Nice. Great work. Which time do we have? 5. Okay. Nice. I think I can do it. All right, last chunk of information for today, and then we're going to stop. Okay? Now we're going to start connecting some dots. Now we know that electrons and lights share some very common similarities. And this is where we're going to start to see how this connects, to your flame test lab that you guys did yesterday. And we're going to start talking about how electrons and color of light are connected. So when an electron is in its lowest energy or its stable state, this is called the ground state. Okay? Electrons want to be here because it's their most stable state, right? You want to be more stable than unstable, I would hope. Okay? So, when we add energy to our electrons, in the instance of our lab yesterday, the flame test lab, we added flame, okay? The electrons become excited, okay? And these electrons are going to start absorbing different wavelengths of light. This added energy causes our amplitude of the electron wave to increase. And then our electrons have the ability to start jumping to other energy levels. Because their amplitude is increasing so much, they have this ability to jump up different energy levels. As I said before, this is incredibly unstable for our electron, and this extra energy is released, okay? And when it is released, our electron goes from our higher energy level to our back down to a lower energy level. And when that happens, different colors of light are released. This is going to start to make sense with the data that you got yesterday for your flame test lab. Okay, I'm hoping this is starting to connect maybe some dots here, that the different elements that you had, okay, had different lights emitted, so different energy. Electrons are jumping from different energy levels. Great analogy by Miss Simpson, one of my favorites ever. Very relevant to yesterday. If you ate a lot of Halloween candy yesterday, you might have gotten a sugar rush, right? And when you have a sugar rush, what happens to you? Anyone? What happens to you? You jittery? Lots of energy, you're jittery, right? Very similar to the electron, right? So if you want to look at this image over here, okay, we have our electron in one of its lower energy levels. We're adding some energy to the electron. Okay, amplitude increases. It has that ability to jump up another energy level. Okay. When that energy is released, we're going to be jumping back down to our original energy level. Similar to when, after your energy was really high from all the candy that you ate, okay, after a certain amount of time, maybe an hour or so, what happens to you? What happens? You crash? Yes? No? Maybe so? Very similar to this concept here. Ooh. Thumbs up, thumbs down, thumbs sideways. This is the beginning to what we're going to break down a little bit more into detail on Monday.